Good evening, friends, and welcome to Sleepytime Tales, a podcast aimed at helping you to get a good night's sleep. Do you find your mind troubled with the stresses of modern life, especially when the lights are out and you're trying to get a restful night? Does your spinning mind keep you awake? Follow my voice down the path towards a good night's rest. Listen to me tell a story that will keep your mind from wandering to your daytime problems, the ones you can't solve right now and will be easier to solve well rested. Listen to my voice and allow yourself to drift, following the twists and turns of the story, but slowly letting go and drifting into sleep. Let my voice wash over you at a comfortable volume and allow yourself to be distracted from the stresses and worries that play on your mind. Whether you need help falling asleep or going back to sleep in the middle of the night, you can trust me to keep you company and help you to wake up tomorrow in a rested state. You may need to try out Sleepytime Tales for a few nights to get used to the slightly strange idea, but I believe it will be well worth your while. I'm here to work with you, to create a safe space, a cocoon in which you can curl up and allow nature to take its course. So settle down, relax, and allow yourself to get lost in my telling of tonight's story. Before we get to tonight's reading, I'd like to ask for a few minutes of your time. Sleepytime Tales is purely a listener-supported podcast. I can only keep it going, I can only pay for the services and tools that I use, and justify the time that I use on it, thanks to the generosity of listeners like you. If you're finding Sleepytime Tales useful, if it helps you to get a restful night and you would like to keep it going out to thousands of insomniacs just like you, and you have the means to help me out, please consider supporting on the Patreon at patreon.com/sleepytimetales. This is monthly support that not only helps me keep the lights on, but also can get you fun bonuses based on your contribution level. So go along there, take a look, and sign up if you're willing and interested. If monthly is a big ask, and I completely understand that, you can make once-off tips through the tip jar on the website. And if you would like to help out without having to do so financially, you can do just as much by telling people about Sleepytime Tales. If someone else you know is struggling to sleep and you think I can help them, just let them know. And that's enough of that. Let's get to the episode. We return once again to Astronomy, the Science of the Heavenly Bodies, by David P. Todd. And we pick up talking about how remarkable the spectroscope was for astronomy. If we pass from sun to star, the triumph of the spectroscope has been everywhere complete and significant. As the spectroscopic survey of the stars grew towards completeness, it became evident that the swarming hosts of the stellar universe are in constant motion through space. Not only athwart the line of vision as their proper motions had long disclosed, but some stars are swiftly moving toward our solar system, and others as swiftly from it. Fixed stars, strictly speaking, there are no such. All are in relative motion. Exact astronomy, by discussion of the proper motions, had assigned a region of the sky towards which the sun and planets are moving. Spectrography soon verified this direction, not only, but it gave a determination of the velocity of a motion of 12 miles per second in a direction approximately that of the constellation Lyra. From corresponding radial velocities, we draw the ready conclusion that certain groups or clusters of stars are actually connected in space and moving as related systems, as in the Pleiades and Ursa Major. Rather more than a quarter century ago, the spectroscope came to the assistance of the telescope in helping to solve the intricate problem of stellar distribution. Kaptein, by combining the proper motions of certain stars with their classification in the Draper catalogue of stellar spectra, drew the conclusion that, as stars, having very small proper motions, show a condensation towards the galaxy. The stars composing this girdle are mostly of the Sirian type, and are at vast distances from the solar system. The proper motion of a star near to us will ordinarily be large, and in the case of solar stars, the larger their proper motion, the greater their number. So it would appear that the solar stars are aggregated around the Sun himself, and this conclusion is greatly strengthened by the fact that of stars whose distances and spectral type are both ascertained, 7 of the 8 nearest to us are solar stars. In 1889, the spectroscope achieved an unexpected triumph by enabling the late Professor Pickering to make the first discovery of a spectroscopic double, or binary star, a type of object now quite abundant. Unlike the visual binary systems, whose periods are years in length, the spectroscopic binaries have short periods, reckoned some cases in days, or hours even. If the orbit of a very close binary is seen edge-on, the light of the 2 stars will coalesce twice in every revolution. Halfway between these points, there are 2 times when the 2 stars will be moving, one toward the Earth and the other from it. At all times, the light of the star, insofar as the telescope shows it, proceeds from a single object. Now photograph the star spectrum at each of the 4 critical points above indicated. In the first pair, the lines are sharply defined and single, because at conjunction, the stars are simply moving athwart the line of sight, while at the intermediate points the lines are double. Doppler's principle completely accounts for this. The light from the receding companion is giving lines displaced towards the red, while the approaching companion yields lines displaced toward the violet. Mizar, double star at the bend of the handle in the Great Dipper, was the first star to yield this peculiar type of spectrum, and the period of its invisible companion is about 52 days. The relative velocity of the components is 100 miles a second, and on applying Newton's law, we find its mass exceeds that of the Sun 40-fold. Capella has been found to be a spectroscopic binary, also the pole star. Spectroscopic binaries have relatively short periods, one of the shortest known being only 35 hours in length. It is in the constellation Scorpio. Beta Aurigae is another whose lines double on alternate nights, giving a period of 4 days, and the combined mass of both stars is more than twice that of the Sun. The catalogue of spectroscopic binaries is constantly enlarging, but thousands doubtless exist that can never be discovered by this method, as is evident if their orbits are perpendicular to the line of sight or nearly so. The history of spectroscopic binaries is one of the most interesting chapters in astronomy, and affords a marvelous confirmation of the prediction of Bessel, who first wrote of the astronomy of the invisible. Find a star's distance by the spectroscope? Impossible, everyone would have said, even a very few years ago. Now, however, the thing is done, and with increasing accuracy. Adams of Mount Wilson has found, after protracted investigation, that the relative intensity of certain spectral lines varies according to the absolute brightness of a star. Indeed, so close is the correspondence that the spectroscopic observations are employed to provide, in certain cases, a good determination of the absolute magnitude, and therefore the distance. To test this relation, the spectroscopic parallaxes have been compared with the measured parallaxes in numerous instances, and an excellent agreement is shown. This new method is adding extensively to our knowledge of stellar luminosities and distances, and even the vast distances of globular clusters and spiral nebulae are becoming known. In fact, but few departments of the old astronomy are left, which the new astronomy has not invaded. And this latest triumph of the spectroscope, in determining accurately the distances of even the remotest stars, is enthusiastically welcomed by advocates of the old and new astronomy alike. Chapter 21. The Story of Astronomical Photography. The most powerful ally of both telescope and spectroscope is photography. Without it, the marvelous researches carried on with both these types of instruments would have been essentially impossible. Even the greatest telescopes of Herschel and Lord Rosse, notwithstanding their splendid record as optical instruments, might have achieved vastly more had photography been developed in their time, to the point where the astronomer could have employed its wonderful capabilities, as he does today. And with the spectroscope, it is hardly too much to say that no investigator ever observes visually with that instrument anymore. Practically every spectrum is made a matter of photographic record first. The observing, or nowadays the measuring, is all done afterward. All telescopes and cameras are alike, in that each must form or have formed within it an image by means of a lens or mirror. In the telescope, the eye sees the fleeting image. In the camera, the process of registering the image on a plate or film is known as photography. Daguerre first invented the process, silver film on a copper plate, in 1839. The year following, it was first employed on the moon. In 1850, the first star was photographed. In 1851, the first total eclipse of the sun, all by the primitive daguerreotype process, which, notwithstanding its awkwardness and the great length of exposure required, was found to possess many advantages for astronomical work. About the middle of the last century, the wet plate process, so called because the sensitized collodion film must be kept moist during exposure, came into general use. And yet astronomers of that period were not slow to avail themselves of the advantages of a more sensitive process, which in 1872, in the skillful hands of Henry Draper, produced the first spectrum of a star. In 1880, a nebula was first photographed, and in 1881, a comet. Before this time, however, the new dry plate process had been developed to the point where astronomers began to avail of its greater convenience and increased sensitiveness, even in spite of the coarseness of the grain of the film. 40 years of dry plate service have brought a wealth of advantages scarcely dreamed of in the beginning, and nearly every department of astronomical research has been enhanced thereby, while many entirely new photographic methods of investigation have been worked out. Continued improvement in the photographic processes has provided the possibility of pictures of fainter and fainter celestial objects, and all the larger telescopes have photographed stars and nebulae of such exceeding faintness that the human eye, even if applied to the same instrument, would never be able to see them. This is because the eye, in 10 or 12 seconds of keen watching, becomes fatigued and must be rested, whereas the action of very faint light rays is cumulative on a highly sensitive film, so that a continuous exposure of many hours' duration becomes readily visible to the eye on development. So supersensitive dry plate will often record many thousand stars in a region where the naked eye can see but one. Perhaps the greatest amplification of photography has taken place at the Harvard Observatory under Pickering, where a library of many 100,000 plates has accumulated, and at Groningen in Holland, where Kaptein has established an astronomical laboratory without instruments, except such as are necessary to measure photographic plates, whenever and wherever taken. So it is possible to select the clearest of skies all over the world for exposure of the plates and bring back the photographs for expert discussion. Of course, the sun was the celestial body first photographed, and its surpassing brilliance necessitates reduction of exposure to a minimum. In moments of exceptional steadiness of the atmosphere, a very high degree of magnification of the solar surface on the photographic plate is permitted, and the details in formation, development, and ending of sunspots are faithfully registered. Nevertheless, it cannot be said that photography has yet entirely replaced the eye in this work, and careful drawings of sunspots at critical stages in their life are capable of registering fine detail, which the plate has so far been unable to record. Janssen of Paris took photographs of the solar photosphere so highly magnified that the granulation or willow leaf structure of the surface was clearly visible, and its variations traceable from hour to hour. The advantages of sunspot photography in ascertaining the sun's rotation, keeping count of the spots, and in a permanent record for measurement of position of the sun's axis and the spot zones are obvious. In direct portrayal of the sun's corona during total eclipses, photography has offered superior advantages over visual sketching in the form and exact location of the coronal streamers. But the extraordinary differences of intensity between the inner corona and its outlying extensions are such that a halation renders a complete picture on a single plate practically impossible. The filamentous detail of the inner corona and the faintest outlying extensions or streamers, the eye must still reveal directly. In solar spectrum photography, research has been especially benefited. Indeed, exact registry of the multitudinous lines was quite impossible without it. Photographic maps of the spectrum by Thollon, MacLean, and Rowland are so complete and accurate that no visual charts can approach them. Rowland's great photographic map of the solar spectrum spread out into a band about 40 feet in length. And in the infrared, Langley's spectrobolometer extended the invisible heat spectrum photographically to many times that length. At the other end of the spectrum, special photographic processes have extended the ultraviolet spectrum far beyond the ocular limit, to a point where it is abruptly cut off by absorption of the Earth's atmosphere. On the same plate, with certain regions of the sun spectrum, the spectra of terrestrial metals are photographed side by side, and exact coincidences of lines show that about 40 elemental substances known to terrestrial chemistry are vaporized in the sun. Young was the first to photograph a solar prominence in 1870, and 20 years later, Deslandres of Paris and Hale of Chicago independently invented the spectroheliograph, by which the chromosphere and prominences of the sun, as well as the disk of the sun itself, are all photographed by monochromatic light on a single plate. Hale has developed this instrument almost to its limit. First at the Yerkes Observatory of the University of Chicago, and more recently at the Mount Wilson Observatory of the Carnegie Institution, where spectroheliograms of marvelous perfection are daily taken. It was with this instrument that Hale discovered the effect of an electromagnetic field in sunspots, which has revolutionized solar theories, the research impossible to conceive of without the aid of photography. When we apply Doppler's principle, photography becomes doubly advantageous. Whether we determine, as Dunér did, and more recently Adams, the sun's own rotation and find it to vary in different solar latitudes, the equator going fastest, or apply the method to the sun's corona at the east and west limbs of the sun, which Deslandres in 1893 proved to be rotating bodily within the sun, because of the measured displacement of spectral lines of the corona and juxtaposition on the photographic plate. In the solar astronomy of measurement, too, photography has been helpfully utilized, as in registering the transits of Mercury over the sun's disk, for correcting the tables of the planet's orbital motion, and most prominently in the action taken by the principal governments of the world in sending out expeditions to observe the transits of Venus in 1874 and 1882, for the purpose of determining the parallax of Venus, and so the distance of the Earth from the Sun. In our studies of the Moon, photography has almost completely superseded ocular work during the past 60 years. Rutherford and Draper of New York, about 1865, obtained very excellent lunar photographs with wet plates, which were unexcelled for nearly half a century. The Harvard, Lick, and Paris observatories have published pretty complete photographic atlases of the Moon, and the best negatives of these series show nearly everything that the eye can discern, except under unusual circumstances. Later lunar photography was taken up at the Yerkes Observatory, and exceptionally fine photographs on a large scale were obtained with a 40-inch refractor using a color screen. More recently, the 60-inch and 100-inch mirrors in the Mount Wilson Observatory have taken a series of photographs of the Moon, far surpassing everything previously done, as was to be expected from the unique combination of a tranquil mountain atmosphere with the extraordinary optical power of the instruments, and a special adaptation of the photographic methods. During lunar eclipses, Pickering has made a photographic search for a possible satellite of the Moon. Occultations of stars by the Moon have been recorded by photography, and Russell of Princeton has shown how the position of the Moon among the stars can be determined by the aid of photography with a high order of precision. The story of planetary photophotography is on the whole disappointing. Much has been done, but there is much that is within reach, or ought to be, that remains undone. From Mercury nothing ought perhaps to be expected. On many of the photographs of the transit of Venus, especially those taken under the writer's direction at the Lick Observatory in 1882, we have unmistakable evidence of the planet's atmosphere. Here again the wet plate process, although more clumsy, demonstrated its superiority over the dry process used by other expeditions. In spectroscopy, Belopolsky has sought to determine the period of rotation of Venus on her axis. At the Lowell Observatory, Douglas succeeded in photographing the faint zodiacal light, and very successful photographs of Mars were taken at this institution as early as 1905 by Slipher. 2 years later, these were much improved upon by the writer's expedition to the Andes of Chile, where 12,000 exposures of Mars were made, many of them showing the principal canali and other prominent features of the planet's disk. At subsequent oppositions of the planet, Barnard at the Yerkes Observatory and the Mount Wilson observers have far surpassed all these photographs. For future oppositions, a more sensitive film is highly desired, in connection with instruments possessing greater light-gathering power, so permitting a briefer exposure that will be less influenced by irregularities and defects of the atmosphere. The spectrum of Mars is of course that of sunlight, very much reduced, and modified to a slight extent by its passing twice through the atmosphere of Mars. What amount of aqueous vapor that atmosphere may contain is a question that can be answered only by the critical comparison of the Martian spectrum with the spectrum of the Moon, and photography affords the only method by which this can be done. Many other ways in which photography has aided research on the asteroid group. Since 1891, more than 600 of them have been discovered by photography, and it is many times easier to find the new object on the photographic plate than to detect it in the sky as was formerly done by means of star charts. The planet by its motion during the exposure of the plate produces a trail, whereas the surrounding stars are all round dots or images. Or by moving the plate slightly during exposure, as in Metcalfe's ingenious method, we may catch the planet at that point where it will give a nearly circular image, and thus be quite as easy to detect, because all the stars on the same plate will then be trails. Photographic photometry of the asteroids has revealed marked variations in their light, due perhaps to irregularities of figure. On account of their faint light, the asteroids are especially suited, as Mars is not, to exact photography from ascertaining their parallax, and from this the Sun's distance when the asteroid's distance has been found. Many asteroids have been utilized in this way, in particular Eros. In 1931 it approaches the Earth within 13 million miles, when the photographic method will doubtless give the Sun's distance with the utmost accuracy. Photographs of Jupiter have been very successfully taken at the Yerkes and Lowell observatories, and elsewhere. But the great depth of the planet's atmosphere is highly absorptive, so that the impression is very weak in the neighborhood of the limb, if the exposure is correctly timed for the center of the disk. The striking detail of the belts, however, is excellently shown. Wood of Baltimore has obtained excellent results by monochromatic photography of Jupiter and Saturn, with the 60-inch reflector on Mount Wilson. Jupiter's satellites have not been neglected photographically, and Pickering has observed hundreds of the eclipses of the satellites by sort of cinematographic method of repeated exposures around the time of disappearance and reappearance by eclipse. The newest outer satellites of Jupiter were all discovered by photography, and it is extremely doubtful if they would have been found otherwise. Saturn has long been a favorite object with the astronomical photographer, and there are many fine pictures in spite of his yellowish light, relatively weak photographically. The marvelous ring system with the Cassini division, the oblateness of the ball, the occasional markings on it, all are well shown in the best photographs. But the call is for more light and a more sensitive photographic process. Pickering's ninth satellite, Phoebe, was discovered by photography, one of the tiniest moons in the solar system. Like the faint outer moons of Jupiter, few existing telescopes are powerful enough to show it. Its orbit has been found from photographic observations, and its position is checked up from time to time by photography. But the crowning achievement of spectrum photography in the Saturnian system is Keeler's application of Doppler's principle in determining the rate of orbital motion of particles in different zones of the rings, thereby establishing the Maxwellian theory of the constitution of the rings beyond the possibility of doubt. For Uranus and Neptune, photography has availed but little, except to negative the existence of additional satellites of these planets, which doubtless would have been discovered by the thorough photographic search which has been made for them, but W.H. Pickering without result. As with the asteroids, so with comets. Several of these bodies have been discovered by photography, none more spectacular than the Egyptian comet of May 18th, 1882, which impressed itself on the plates of the corona of that date. Withdrawal of the sun's light by total eclipse made the comet visible, and it had never been seen before, nor is it known whether it will ever return. In cometary photography, much of the same difficulties are present as in photographing the corona. If the plate is exposed long enough to get the faint extensions of the tail, the fine filaments of the coma or head are obliterated by halation and overexposure. No one has had greater success in this work than Barnard. His photographs of comets, particularly at the Lick Observatory, are numerous and unexcelled. His photographs of the Brooks comet of 1893 revealed rapid and violent changes in the tail, as if shattered by encounters with meteors. And the tail of Halley's comet in 1910 showed the rapid propagation of luminous waves down the tail, similar to phenomena sometimes seen in streamers of the aurora. Draper obtained the first photograph of the comet spectrum in 1881, disclosing an identity with hydrocarbons burning in a Bunsen flame. Also bands in the violet due to carbon compounds. The photographic spectra of subsequent comets have shown bright lines due to sodium and the vapor of iron and magnesium. Even the elusive meteor has been caught by photography, first by Wolf in 1891, who was exposing a plate on stars in the Milky Way. On developing it, he found a fine, dark, nearly uniform line crossing it, due to the accidental flight across the field of a meteor of varying brightness. Since then, meteor trails have been repeatedly photographed, and even the trail spectra of meteors have been registered on the Harvard plates. At Yale in 1894, Elkin employed a unique apparatus for securing photographic trails of meteors. 6 photographic cameras mounted at different angles on a long polar axis, driven by clockwork. The whole arranged so as to cover a large area of the sky where meteors were expected. When we pass from the solar system to the stellar universe, the advantages of photography and the amplification of research, due to its employment as accessory in nearly every line of investigation, are enormous. So extensively has photography been introduced that plates, until a slight extent films, are now almost exclusively used in securing original records. Regrettably so in the case of the nebulae, because the numerous photographs of the brighter nebulae taken since 1880, when Draper got the first photograph of the nebula of Orion, are as a rule not comparable with each other. Differences of instruments, of plates, of exposure and development, all have occasioned differences in portrayal of a nebula which do not exist. When we consider faithful accuracy of portrayal of the nebula for purposes of critical comparison from age to age, many of our nebula photographs of the past 40 years, fine as they are and marvelous as they are, must fail to serve the purpose of revealing progressive changes in nebula features in the future. Roberts and Common in England were among the first to obtain nebula photographs with extraordinary detail. Also the brothers Henry of Paris. As early as 1888, Roberts revealed the true nature of the great nebula in Andromeda, which had never been suspected of being spiral. And Keeler and Perrin at the Lick Observatory pushed the photographic discovery of spiral nebulae so far that their estimates filled the sky with many hundred thousands of these objects. In the southern hemisphere, the 24-inch Bruce telescope of Harvard College Observatory has obtained many very remarkable photographs of nebulae, particularly in the vicinity of Eta Carinae. But the great reflectors of the Mount Wilson Observatory, on account of their exceptional location and extraordinary power, have surpassed all others in the photographic portrayal of these objects, especially the spiral nebulae, which appear to show all stages in transition from nebula to star. No less remarkable are the photographs of such wonderful clusters as Omega Centauri, a perfect visual representation of which is wholly impossible. Into comparison of the photographs of clusters has afforded Bailey of Harvard, Shapley of Mount Wilson, and others the opportunity of discovery that hundreds of the component stars are variable. What is the longest photographic exposure ever made? At the Cape of Good Hope, under the direction of the late Sir David Gill, exposures on nebulae were made, utilizing the best part of several nights, and totaling as high as 17 or even 23 hours. But the Mount Wilson observers have far surpassed this duration. To study the rotation and radial velocity of the central part of the nebula of Andromeda, an exposure of no less than 79 hours total duration was made on the exceedingly faint spectrum, and even that record has since been exceeded. The eye cannot be removed from the guiding star for a moment while the exposure is in progress, and this tedious piece of work was rewarded by determining the velocity of the center of the nucleus as a motion of approach at the rate of 316 kilometers per second. And I think I'm going to leave it there because we move into a whole other topic on the next section. The thing that I find really fascinating about this is they didn't know yet what galaxies were. They thought spiral nebulae were the formation of stars, like cloud nebula are. This is really amazing reading. And if you're as fascinated as I am by it, you can, as always, pick it up on Project Gutenberg at the link in the show notes. Thanks again for joining me on this episode of Sleepy Time Tales, a podcast designed around a bedtime story to help you to get a restful night. New episodes will be released every Sunday night to give you something fresh to help you rest in a new week. But make sure to follow or subscribe in whatever service you use so that you get your new episodes whenever they come out. Good night and sweet dreams.